Welcome. Today is a lecture devoted to diffusion. And phenomena in ultra-rarefied gases. Well, let's start with the first one. Oh, not diffusion, but that's mistake. Brownian motion. Brownian motion. Let's start with the first one, a Brownian motion. Brownian motion is, I would say, an attempt to visualize motion of molecules. In order to do this, the main problem to visualize motion of molecules is that molecules are too small. That's why you can't even see molecules in an optical microscope. You can see molecules and atoms in electronic microscope, but this kind of equipment is too expensive, and in order to have some kind of a observation, it would be preferred to have some kind of an object which we can see in an optical microscope, but this type of object can also move like a molecule. And such an object can be a small droplet which moves in gas. Small droplet. The size of a single droplet can be much larger than size of molecules. At the same time, this droplet is not too large, and this droplet should feel the motion of molecules as they collide with it and slightly change its velocity. And if we look at the motion of this droplet, it will show us that the number of collisions is really large, and it will move as in short lines which connect to each other like this. So we will observe some chaotic motion of this droplet. Okay. Since we are having a large number of collisions, the motion of this droplet will be similar to the process of diffusion. As you know, the process of diffusion is characterized by a large number of collisions, which prevent molecules from moving in straight lines. So, due to collisions, they also exhibit similar kind of a behavior, and they move in these zigzag lines. And due to the large number of collisions, an average distance traveled by the molecule should be proportional, the squared average of the distance should be proportional to time. I would like to repeat an argument for this, because it's very important. And the argument is as follows. Let's look at one of the coordinates of our, okay, let's look at our vector. And let's assume that between the collisions, this particle, droplet, or a molecule, it doesn't matter because we are considering this droplet as a very large molecule. Moves over the same distance which is equal to lambda. And lambda here is mean free path. Of course, I am doing a simplification because, as we have considered during the previous lecture, the distance traveled by any kind of an object between collisions is a random number, is a random value. And when I say that this distance equals to lambda, I'm doing a simplification already. But nevertheless, This simplification allows us to understand the main principles of this motion. So between the collisions, I have this kind of expression. And also, a time between two subsequent collisions is equal to lambda over average or mean speed of this particle. Lambda over mean speed. So that means that if I square this equation, I get that I plus 1 squared equals to Ri squared plus lambda squared plus 2Ri lambda. And here we have a scalar product of two vectors. Then I take an average of both of these parts and get the following. And for the last part of this equation, I assume that the direction of the displacement of the molecule after each collision is random. That means that this lambda can have the equal probability of opposite direction, and due to this, since lambda is independent of Ri, I get that this average is equal to the product of averages, and which is 0. So what I have is that during each of the collisions, between collisions, the squared average of the distance traveled by a molecule increases by lambda squared. So if I look at an average squared traveled distance as a function of time, it will be equal to n multiplied by lambda squared, where n is a number of collisions, and this n can be found by dividing the time by tau. So this is time divided by tau multiplied by lambda squared. And this gives me altogether, this gives me lambda V average multiplied by t. Or if I remember the previously derived formula that the diffusion coefficient is given as 1/3 multiplied by lambda multiplied by mean speed, this would give me 3 dt. Of course, I would not too much believe into this coefficient because I have done a pretty drastic simplification of the considered problem. That's why this coefficient is questionable, but this part is true. So indeed, the average, the squared average of the distance traveled by a particle is product of diffusion coefficient by the time. And more, okay, the precise relation is that r squared is actually equal to 6 dt, and this equation can be obtained after a rigorous calculation, which I am not going to be doing today, but the result of the rigorous calculation will be as follows. This is main equation of Brownian motion. Or if you consider a motion along each of these axes, then along each of axes it will give us 2 dt. So this is x squared average, y squared average, and z squared average gives us 2 dt. And of course, R squared average can be calculated as sum of these three averages. So now I have perfect consistency between these formulas. Okay, this is the first equation you should understand about Brownian motion. There is another one, which is typically called Einstein's Molokovsky law. Or sometimes just an Einstein law of Brownian motion or diffusion. It turns out that you may consider the following problem. Let's assume that you apply some force onto the particle. Then if we have motion in vacuum, then you know that according to the second Newton's law, the acceleration of the particle should be equal as force divided by its mass. But due to the presence of gas around this molecule and multiple collisions of gas with this particle, there is a resistance from the medium. And due to this resistance, so in gas or other medium, instead of this, so this is in vacuum, without any other forces present, but in gas, you have viscosity, you have friction force, okay, you have some kind of a resistance of this medium to the motion of this particle. So instead of this, I would say that the particle would move with this velocity, which is proportional to the applied force, Bf. And B, coefficient B, is typically called mobility. Mobility. It says that if this B coefficient is large, then particle would move with higher speed when you apply the same force. So you can say that this particle is mobile. So you apply some force and this particle starts moving at a great speed. But if it is low, then you can say that the resistance of the medium is very large and you need to apply larger force in order to achieve some kind of a noticeable speed of this particle. Well, of course, when I say that V equals to B multiplied by F, I am doing another kind of a simplification. Of course, I understand that due to the collisions of this particle with molecules, its motion will be a superposition of a random motion due to the collisions with gas particles and drift motion, so at a constant velocity. So total motion of this particle would be a superposition of two different types of motion. That's why when I say about this law, I mean that average velocity of this particle is equal to B multiplied by F. Well, that means that without any kind of external force, average velocity would be 0. And this is the truth. So if you consider the motion that we have considered previously here, motion due to the collision of this particle with molecules of gas, then, okay, we have a non-zero squared average of the displacement of the molecule, but at any point of time, average displacement of this molecule without square, so average vector, is equal to Ri plus average lambda. And as we know, this lambda has random direction, No direction is being preferred over other direction. That's why this average is 0. And we can say that Ri plus 1 equals to Ri, and then we can continue this further, and we get that this vector is equal to the displacement at the initial point of time. So I can write the displacement over time is 0. That's why average velocity of the particle which is undergoing collisions with other molecules is is 0. So everything here coincides. But when you apply an external force, you add an additional component of force, you add this ordered type of motion, and you would have some kind of a displacement due to this external force. And it turns out that actually the mobility is related to the diffusion coefficient. At first, it seems, it's too difficult to predict that mobility would have some relation to the diffusion coefficient, because mobility is related to the situation when you apply an external force, while the diffusion coefficient describes the case when there is no external force being applied, when you only have collisions with other molecules. But nevertheless, the existence of mobility and the existence of this diffusion has the same origin. The same origin is that a collision with particles. If you don't have any collisions with molecules of gas, we would have an accelerated motion of a particle. But due to the collisions with other molecules, we have a constant velocity motion, and the reason behind this is the collisions with other molecules. So that's why there is a relation, because these two phenomena, they have the same origin. In order to determine the relation between the mobility and the diffusion coefficient, I will consider the following problem. Let's say we have a large number of external large particles dropped into the gas or into liquid. And let's say I apply the same force F to each of these particles. Often this force can be considered as a gravitational force. So we can assume that all of these particles are under influence of gravitational force. And then I consider a distribution of these particles as a function of z coordinate. So as a function of height, as a function of altitude. According to Boltzmann distribution, the number density of particles would depend on z as follows. It would be equal to n0, number density at 0 altitude, multiplied by the exponent of minus u divided by kBt, where u is the potential energy of particles due to the presence of this force. So u as a potential energy is given as Fz. So that's why I have n of z equal to n0 multiplied by exponent minus Fz over kBt. Okay, I now have some kind of a steady state distribution of particles in my vessel. And let's consider this distribution on a microscopic level. First of all, I see that the number density increases as we decrease the altitude. So if I plot number density as a function of altitude, it would give me this type of a function. That means that in a higher altitude, we have lower number of particles, while at the lower level, I have more particles. Due to the difference in the number density of these particles, there is according to Fick's law of diffusion, there is a current of these particles moving from the bottom to the top. So there is a current which wants to achieve an equilibrium distribution where all of the number densities are independent of z. So the current of these particles, the number of particles which go from the bottom to the top per unit of time, per unit of area, is equal to diffusion coefficient multiplied by the derivative of n over z. Okay, so when I minus dn over dz, and this is minus dn multiplied by f over kbt. Okay, here it goes plus, because minus. So I take a derivative of this exponent. The derivative of exponent gives me the same exponent. That's why I have n here. And also, due to the chain law, I need also to take a derivative of the expression in the exponent. And when I take the derivative of this over z, I get f over kbt. And that is being eliminated from here. So this is dn multiplied by f of kbt. But since this distribution, this Boltzmann distribution, is an equilibrium steady-state distribution, that means that there should exist another current of particles which moves in the downward direction. And this current is due to the drift motion under the action of the constant force F. So as I said previously, when you apply a constant force F, then there would be a downward motion of the particle. So the current in the downward direction is equal to the n multiplied by v, where v is an average velocity of these particles due to the applied force. And this can be related to the mobility as n, b, f. Okay, in the equilibrium, these two currents should be equal to each other. That's why I get dn f over kbt equals to n multiplied by b multiplied by f. Now I eliminate all of the common factors in the left and right hand side of this equation and get the diffusion coefficient is equal to b multiplied by kbt. This is Einstein's Molokovsky law. It's often also called just Einstein law or the relation between diffusion coefficient and mobility. It's a very important equation, very important law. It's one of the particular cases of a more general fluctuation dissipation theorem. Which describes many important phenomena such as spontaneous emission and noise and has many other applications. But when applied to the Brownian motion, this fluctuation dissipation theorem gives this relation between the diffusion coefficient and the mobility of particles. So now I would like to conclude the topic about diffusion, or about Brownian motion. And give a small digest. Okay. So, Brownian motion is described by two main formulas. This is squared displacement along one of the axes, or if you prefer, average displacement from a certain point. And the other is the relation between diffusion coefficient and mobility. Okay. The combination of these two laws allows us to determine important constants like Boltzmann constant. Because this mobility coefficient can be determined theoretically from theoretical consideration for the motion of the particle in the viscous fluid, then there is a so-called Stokes formula which relates this mobility coefficient to the properties of the fluid. And then you can measure, you can do an observation of particles, or you can do the observation of the number density of different particles, as was performed by Perrin. And from these observations, you would be able to determine the Boltzmann constant and therefore all of the other important constants for gas, like Avogadro number and everything else. So the observation of the motion of a so-called large molecule allows you to probe the microscopic properties of gas and the macroscopic properties of unobservable molecules at that time. So at that time, when these experiments were performed, the motion of molecules was not visible, and only due to the experiments of Perrin, we were able to determine important quantities related to the molecular structure of gas. Okay. Now let's continue. And the next part of this lecture will be devoted to ultra-rarefied gases. At the start of the previous lecture, I have said that when you open a flask of perfume or other smelly substance, then the scent of the substance would propagate to other points in space, not immediately, as you would, I think, as you would suggest from the average thermal speed of molecules, but it would take a long time for the scent to go from this part of the room to the other part of the room. And the reason for this is that each molecule experiences a large number of collisions, and that's why for a certain molecule to propagate a distance from one corner of the room to another corner of the room, this molecule should experience a large number of collisions, and due to this large number of collisions, the time of travel increases dramatically. But what would happen if we decrease the density of gas to such low quantities that the mean free path, L, would be comparable to the size of the room, to the characteristic size of the room, or even less, or even more than that. That means that this picture is no longer valid, and a molecule would experience no collision inside this room. So mostly all of the collisions of the molecules of gas would happen only with walls in the room, or side walls in the vessel, if you consider motion of gas in the vessel. In other words, the motion of this particle would be not diffusive, but so-called ballistic motion, ballistic regime. So in the ballistic regime, there would be no collisions in between, and particle would move freely from one point of the room to another point of the room until they collide with the sidewalls. In the ballistic regime, mean free path of the molecule is no longer determined by the number density of gas molecules in the room or in the vessel. L, mean free path, is determined by the size scale of the vessel. So I can even say that L is on the same order as a characteristic size of the vessel or characteristic size of the room. This condition is often called physical vacuum. Physical vacuum. So when you have this change in the properties of motion of molecules in your vessel or in your room, then you have achieved the condition for the physical vacuum. One interesting peculiarity of the physical vacuum condition is that the pressure of the gas or the number density of the molecules of the gas when physical vacuum condition is achieved is dependent on the size of the vessel or the size of the room. And as a result, it is sometimes possible to achieve physical vacuum conditions even at atmospheric pressure. You just need, for your vessel or for your characteristic size of the room, or well, of a cavity where your molecules of gas are moving, for the size should be of the same order as the mean free path of the molecules at the atmospheric pressure. And then you get a so-called physical vacuum condition. Physical vacuum condition can be achieved in a small pores. So it can be achieved in some kind of a porous substance which has small pores, and these pores are so small that molecules of gas move from one side of the pore to the other side of the pore without experiencing any collisions. And I would say that in Earth, there are these small pores, and they influence the motion of gas in Earth and allow Earth to breathe. When you change the temperature, the concentration of molecules in these pores would change. And as a result, there would be an exchange of gas between these pores and the atmosphere, which would allow the so-called for the Earth to breathe, for the gas to be changed in these pores. So when you increase and decrease the temperature of ambient air, there would be a gas exchange. So this is a very important condition. Now let's consider a physical phenomena which happen when you get into the ballistic regime of the motion of molecules. Now, first of all, let's assume that we have two vessels connected by a small aperture. And molecules can move from one vessel to another vessel, and there is no collision. No collisions happen around this aperture, while collisions may happen in each of these vessels. So I can assume that the number density of molecules in each of these vessels is quite large, but I assume that the mean free path of these molecules is much larger than the radius of aperture, which connects these two vessels. Under these collisions, it would be impossible to establish a hydrodynamic flow. So previously we have studied hydrodynamics, and we have considered problems like follows. We have some vessel and we have an aperture, and the pressure here is lower than the pressure inside the vessel, and due to the difference of pressures there would be a flow of molecules from the vessel to the outside environment. But due to the absence of collisions, each molecule in this situation would move independently, and there would be no hydrodynamic flow. So it would be impossible to establish hydrodynamic flow. And we are in the situation when we can consider motion of each molecule of gas independently through this orifice or through this aperture. Now let's determine an equilibrium condition between these two vessels. Let's assume that gas here is kept at temperature T1 and pressure P1, while gas in the second vessel is kept at temperature T2 and pressure P2. As we have derived previously, the number of molecules which go from one vessel to another vessel is given by the following equation. So this is G, number of molecules which go from the first vessel to the second vessel per unit of time, is given as number density multiplied by an average, by mean speed, mean thermal speed of molecules, divided by 4, multiplied by an area of the orifice. The same could be written for the current of molecules which move from the second vessel to the first vessel. Here I write N2 multiplied by mean speed 2 over 4 multiplied by this area. In the equilibrium, these two currents are equal to each other. That's why I get that N1 multiplied by Vn average equals to N2 multiplied by V2 average. And finally, I need to relate these number densities to the macroscopic parameters such as pressure or temperature. And here I use two laws. First of all, I use that pressure is related to the number density as NkBT. And the other is that the mean thermal speed is given by the following expression. This is 8 kBT over Pm, where m is mass of a single molecule. From these two expressions, I get that n equals to P over kBT, or I can say that this is proportional to P over T. The other here is constant, is a constant of proportionality. And for the mean speed, I can write that mean speed is proportional to square root of the temperature, because Boltzmann constant and mass of the molecule and other constants here are independent of the macroscopic condition. They don't depend on pressure, they don't depend on temperature. So the only dependence on macroscopic conditions is the proportionality to the square root of T. And that's why when I go to this expression, I get that NV average is proportional to P over T multiplied by square root of T. And this is P over square root of T. And due to this, the condition for the equilibrium between these two vessels would be P1 over square root of T1 equals to P2 over square root of T2. Okay, the main consequence of this formula is here we demonstrate that, well, previously I have said many times that the order of establishment of equilibrium is as follows. First, mechanical equilibrium is established. This is the fastest process when the mechanical equilibrium is being established. When we have two vessels, mechanical equilibrium implies that pressure is the same. And secondly, thermal equilibrium is being established. T1 equals to T2. But when we have a connection only through this small orifice, and let's assume that we have here a thermal insulating wall here, there is no heat exchange through this wall, then it means that instead of this order of establishment of equilibrium, only one type of equilibrium can be established when P1 over square root T1 equals to P2 over square root T2. And we can keep these two vessels at different temperatures, and after some time there will be an equilibrium according to this law. And this is called Knutson Effect. So Knutson effect is an effect that you may have an equilibrium condition without mechanical equilibrium, when two vessels can communicate only through a small orifice or only through a small pipe, and they have different temperatures, then the equilibrium is established without mechanical equilibrium condition. Okay, now let's have a small break for 5 minutes and continue after the break. Okay, let's continue. The next problem which we would consider is we have two different vessels connected by a quite large pipe with the length L, but the pipe has a very small radius r, which is much smaller than mean free path of molecules in both of these vessels. I want to find the amount of gas which flows from the vessel with higher pressure to the vessel with lower pressure. Now, previously we have considered the similar problem, but under the condition when the radius of the pipe was much larger than mean free path of molecules. And the result was Poisson Equation. Here I assume that the pressure difference is very small compared to the pressure in order to for the density of the gas to be approximately constant everywhere. So this formula is valid in such conditions. Now let's solve the similar problem in the so-called ballistic regime when we have connection between these two vessels with a large but the pipe which has very small diameter. Okay. First of all, let's consider a type of motion of each of the molecules inside this pipe. There are no collisions between molecules inside the pipe, but there are collisions with side walls of this pipe. Due to these collisions, the molecule can move forward and move backward, so the motion of this molecule is chaotic. But this motion is pretty much similar to the motion of molecules in the process of diffusion. So we can ascribe a diffusion coefficient to this type of motion. First of all, we need to determine a mean free path of the molecule inside the pipe. Since there are no collisions between molecules, then inside the pipe, mean free path is determined by a characteristic size of this pipe. I would say that mean free path is some kind of a coefficient multiplied by the diameter of the pipe, twice the radius. But I don't know the coefficient, and for this simplification purpose, I would assume that this coefficient is 1. So I assume that the mean free path is equal to the diameter of the pipe. And then I calculate the diffusion coefficient as 1/3 multiplied by mean free path multiplied by mean thermal speed of molecules. And this gives me 2r/3 multiplied by this mean speed. And then, due to the difference in pressures between the molecules, I can calculate number densities of the molecules inside these two vessels as N1 as P1/kBt1 and N2 as P2/kBt2. Okay, the temperature is the same, that's why I can write over kBt everywhere. And there is difference in number densities. And we have a diffusion from one vessel to another vessel. And the number of particles, according to Fick's law, which move from one vessel to another, is given as follows. dN/dt is equal to well, to the cross section of the pipe, PR squared, multiplied by the number of molecules by unit of cross section by unit of time, which is d multiplied by derivative dn over dx, where x is an axis which is directed from the first vessel to another vessel along the pipe. Okay, since this flux of particles is constant in every cross section, then I can assume that dn over dx is constant. dn over dx is constant, and this is equal to n1 minus n2 divided by L. And from this I get that the number of particles moving from one vessel to another vessel per unit of time is given as pi r squared multiplied by diffusion coefficient 2r over 3 multiplied by mean speed multiplied by n1 minus n2 over L. Now here I insert the equations for number densities. So I get okay. Well, according to the Poisson equation, so we are going to compare this formula to the Poisson equation. The volume of gas transferred between these two vessels would be PR to the power of 4 over 8 eta L multiplied by delta P, so P1 minus P2. And what I see from here is, okay, as in here and in here, the flow of the particles is proportional to the pressure difference, P1 minus P2, divided by L, delta P over L. At the same time, this flow is proportional to the force power of the radius, while this flow is proportional to the third power of the radius. So we have indeed different laws which describe the motion of particles in the ultra-rarefied regime and in the regime when we can assume that hydrodynamics is valid. The hydrodynamics is valid when the mean free path of each molecule is much lower than the characteristic sizes of pipes and vessels. But in here, we have this. Okay, for the next part, I'm going to consider thermal conductivity in the ultra-rarefied regime. Now let's assume that we have top and bottom side walls of the vessel, and while top part of the vessel is kept at temperature T1, the bottom part of the vessel is kept at temperature T2. And we assume that we are in the condition of physical vacuum. The distance between these two is equal to L, and this L is lower than mean free path of the molecules. So we can assume that molecules move from one to another without any collisions in between. Okay, the collision between the particle and the sidewall is a very complicated process. In this collision, particle is scattered randomly in a random direction and at random velocities. So actually the sidewall of the vessel consists of the molecules, and these molecules are also in the thermal motion, so that's why the colliding particle would feel the thermal motion of molecules of the sidewall. For the simplicity, we are going to adopt the following simplification assumption, and the assumption is as follows: that after the collision, the average squared average of the speed of the particle is given by the Maxwell distribution. So after the collision, I assume that V squared average is equal to 3 kb T over m. So after each collision, so when the particle is reflected from this sidewall, its distribution for velocities is Maxwell's distribution with the temperature T1. After the collision with this sidewall of the vessel, the distribution changes again, and we have Maxwell distribution with the temperature T2. Now we are going to determine the heat flux in this system. So the amount of energy transferred from the bottom to in the upwards direction per unit of time is as follows. Here I need to multiply the energy of each particle, which is mv squared over 2, by the number of particles which have the same this velocity v, moving from the bottom to the top. So, and this is given as nv multiplied by v over 4, not over 4, but over 2. Why over 2? The reason why I change coefficient 4 to 2 is that after the collision with this bottom sidewall of the vessel, there would be no particles moving in the downward direction. This direction is prohibited. That's why I multiply the number density of particles having this velocity v by velocity v and dividing over 2. Okay, so now I have an integral mv cubed over 4 multiplied by nv, and nv is given by the Maxwell distribution for speeds, and this is a normalization constant multiplied by 4 pi v squared multiplied by exponent minus mv squared over 2 kbt multiplied by dv. Okay, the same is valid for the flux of the particles from the top plate to the bottom plate. So here I have T2, and here I have exactly the same integral, but with T1. Okay, let me see. And the constants should be different. Okay, I have made a small mistake here. I would like to correct it now. So for the energy flow from the bottom plate to the top plate, I have the following expression. The sum of mv squared over 2 multiplied by the density of particles which move in the upward direction multiplied by v and divided by 2. And here is number density of the particles moving in the upward direction multiplied by the following integral. mv cubed over 4. And now I then multiply by the Maxwell distribution for speeds. Multiply by constant by 4 pi v squared by the exponent of minus mv squared over 2 kb t2 multiplying by dv. Okay, so this is the integral, and for the flux of the energy from moving in the downward direction, I have the similar integral, but with the difference, with the different number density of particles moving in the downward direction. mv cubed over 4 multiplied by the same constant by 4 pi v squared, and then exponent minus mv squared over 2 kb t1 multiplied by dv. Okay, but what I don't know is how these number densities are related to the total number density of the gas in this vessel. First of all, I know that n, total number density, is the sum of number densities of molecules moving in the moving to the top and moving to the bottom. And to determine the relation between these number densities, I need also to calculate the average number of particles moving in the upward and downward direction. In the steady-state regime, these current densities of particles should be equal to each other. Okay, and this gives me the following, that n upwards multiplied by average thermal speed of these molecules divided by 2 equals to n downwards multiplied by average thermal speed of these molecules divided by 2. So V upwards, V downwards. And the first thermal speed, the thermal speed of molecules moving in the upward direction, is proportional to the square root of T2, while the mean speed of molecules moving in the downward direction is proportional to the square root of T1. And that means that, okay, let's continue here. That means that n upwards multiplied by square root of T2 equals to n downwards multiplied by square root of T1. So n upwards to n downwards equals to square root of T1 over square root of T2. And these two number densities are related to the total number density as follows. Okay, now let's calculate this integral. The normalization constant can be determined from the condition, from the normalization condition as follows. Or we can write that C is equal 1 over the integral of 4 pi v squared exponent minus mv squared over 2k bt dv. After I insert this constant C into that integral, I get that the flux of energy in the upwards direction is n upwards multiplied by the following ratio of integrals. Here I have mv to the power of 5 divided by 4, so here these two are eliminated, multiplied by pi, multiplied by the exponent of minus mv squared by 2kb t2 dv, and here I have an integral for 4 pi v squared, the same exponent, okay. Previously I have considered the topic of calculation of these integrals. I have introduced a so-called f functions for the calculation of these integrals. Now I am going to use these formulas to calculate this integral. Okay, I have introduced the function f n of alpha, which was determined as an integral from 0 to infinity of the v to the power n multiplied by exponent of minus alpha p squared dv. Let me look up in my notes where this integrals are. I have the following. F0 is 1 over 2 by pi over square root of a. F1 is 1 over 2a. And also I have the following relation, that f of n is equal to n minus 1 divided by 2a multiplied by f n minus 2. Of course, it's at the same a's. So here I have f of 5, and in the denominator I have f of 2. So I need to calculate f of 5. F of 5 of a is equal to 5 minus 1, which gives me 4. 4 over 2a multiplied by f of 3 of a, and then I continue. F of 3 by this formula again is given as 2 over 2a multiplied by f of 1 of a, and altogether it leads to, this gives me 2 over a squared multiplied by f of 1. 1 over 2a. So this is 1 over a cubed. This is 1 over a cubed. The next is f of 2 as in the denominator of this integral. F of 2 of a is given as 1 over 2a multiplied by f of 0 of a. So this is 1 over 4a multiplied by square root of pi over a. Okay, now I make use of this f5 and f2 to calculate the integral. Which one should I erase? I think since I have already the formula for P for the flux of thermal energy here, I can completely erase these equations. So now I continue for P upwards. This is n upwards multiplied by Pm f of 5 4 minus m over 2kBt. And in the denominator I have 4 pi multiplied by f of 2 for the same coefficient. Okay, here I have T2. I eliminate this pi. I also use that n upwards is n multiplied by square root of T1 over square root of T1 plus square root of T2. And here, okay, 1 over a cubed, m over 4, 1 over a cubed. This is, okay, here I have plus, because here I have m over 2kBt cubed. And here I have 1 over 4a square root of, so this is 1 over 4m over 2kBt multiplied by square root of pi over square root of a. So this gives me m over 2kBt here. So I have a 3-level fraction. Now I continue calculations from here. So this is n square root of T1 divided by square root of T1 by square root of T2. Okay. I eliminate this 4 with this 4. Well, now I'm just doing a straightforward manipulation with fractions. So here I have m multiplied by 2kBt over m cubed. Here I have 2kBt over m with this square root of pi multiplied by 2kBt over m. Now I'm doing the next step. Next step is n square root of T1 square root of T1 plus square root of T2. Okay, now I have forgotten. Here I have T2 all everywhere. T2. And now as I continue, I get here m multiplied by 2kBt cubed over m cubed. Now I'm just reversing the denominator. So I am multiplied by m over 2 kb T2. And with the square root, I do the same. So I have square root of m divided by pi multiplied by square root of 2 kb2. Okay, so now I'm starting elimination so here I have m squared, and here I have m cubed. After I eliminate this, only m is left over. And now I eliminate this m with this one inside the square root, and get m in the denominator of the square root. For these temperatures, 2 kBTs, so I have cubed, I have linear part, so after I eliminate this, this would be the second power, and then, okay, then I get the following. I take only one of these, of the squares inside the square root and get the following. 2 kb T2 multiplied by square root of 2 kb T2 over pi m. Okay, so I can write it like this. N multiplied by 2 square root of kb2 kb T1 T2 over square root of T1 plus square root of T2. And this is expression which is independent of the direction of the flow, and multiplied by 2 kb T2. And now for the total total energy flux between these two plates, I have the following. I think we are very close to the final result. The total power which is being transmitted between the high temperature and low temperature plate is as follows. Oops. This is it. Or the effective thermal conductivity coefficient is given by this. Effective thermal conductivity coefficient. As you see from this formula, we get that thermal conductivity coefficient in the ultra-rarefied case is proportional to the number density of molecules. While, as I have determined previously, look at the seminar presentation, that for the gas not in the rarefied condition, the thermal conductivity coefficient is independent of number density, or independent of temperature, or independent of pressure, actually. Not temperature, but pressure. It's independent of pressure. That means that the thermal conductivity coefficient changes with the number density of particles as follows. Okay, if we have only slight difference between temperatures T1 and T2, I can approximately say that this thermoconductivity coefficient is given as follows. Okay, have I not forgotten anything here? Mass. There was somewhere mass and it was eliminated. Mass should be here in the denominator. Yeah. It's here, multiplied by here. Mass is inside this equation, but after I got it to this stage, I have forgotten pi and m, so I have to add square root of pi m here. Now I think this is a correct formula for the thermoconductivity coefficient. And as you see, when you go to the ultra-rarefied case, the main message of this lecture is that when you go to the ultra-rarefied case, the behavior of molecules changes drastically. And first of all, there are no collisions, which means that mean free path is determined by the characteristic size of the vessel. At the same time, some laws, like independence of the thermoconductivity or viscosity coefficient from the pressure, are no longer valid in the ultra-rarefied case. Because in the ultra-rarefied case, you have too little molecules to carry heat. And for this reason, the heat conductivity coefficient is proportional to the number density of molecules. Also, as I have shown previously, the exchange of molecules between two vessels becomes very different from the case when we have a hydrodynamic case. The flow of the molecules is proportional to the cubed radius of the orifice instead of the force power of the radius of the orifice of the tube, which connects the two vessels. So I think that is it. We are close to the finish, and thank you for your attention.